Okay, hello again everyone. Today we are going to be talking about another interesting electrical device called the capacitor. As you can see here, I have samples of what a capacitor looks like. Now they come in various shapes, sizes, all right? Matter of fact, I will show you a brief clip. Okay. As you can see, there's various types of capacitors, shapes and sizes. There's polyester film capacitor, there's a ceramic capacitor, there's the electrolytic capacitor, the tantalum capacitor, and the polyester. Also, pay attention to the size of these capacitors. They are almost on a micro level. This is just a glimpse at the future of where capacitors are going. Okay, some of the basics of capacitors are the types and the symbols that accompany them. First type we have is what we call the fixed capacitor. This is a symbol that accompanies the fixed capacitor. Fixed meaning that the value is steady, it's constant. Okay? Second, we have what is called the variable capacitor. This is a symbol for the variable capacitor. It is just like the fixed symbol, except that it has an arrow through it, indicating that it could be varied. Third, we have the electrolytic capacitor. And this is a capacitor that has positive terminal and a negative terminal. Okay, we'll talk more about that in another class. Let's go ahead and look at the units for capacitance. Farad is the unit that is used. Sometimes we deal with the microfarad, and most times we are going to be dealing with the microfarad. You could either write out the word microfarad or you could just put mu f. Okay, we borrow this from the Greek alphabet. At times you may encounter what is called a picofarad. And you can just write it as PF. Next we're going to look at what does a capacitor do. Alright, hello again everyone. As you can see, we have functions of a capacitor and also the construction of the capacitor. Let's talk first about the function. Regardless of the size of the capacitors, they all do the same function, and that is to store an electric charge. Capacitors are found in just about almost all our electrical and electronic devices that we have today. I have a series circuit here. My switch is here. The moment I close this switch, a number of charges form on these two plates of the capacitor. On one side it's positive, on the other side it's negative. And it simply remains that way. Because one of the things you will come to understand about a capacitor, because one of the things that you come to understand about a capacitor is that it blocks DC current, but it allows AC current. Let's go ahead and take a look at the construction of the capacitor. As you can see, we have two metal plates. In the center here, this blue area is what you call the dielectric. Now the dielectric is an insulating material, any kind of insulation material. Sometimes even air is used as the dielectric. Here we have our wire, which is used to connect in the circuit. And when this is connected, like I said before, it builds up positive charges on one plate and negative charges on the other plate. I'll talk a little bit more about the function of the capacitor and how it stores the charge and how long it takes to store the charge. We'll do that next. Hello again. We are now going to look at the transient response of the capacitor. Now, what is the transient response? It is the response of current and voltage in a circuit immediately after a change in applied voltage. Now, that applied voltage will come in when I close the switch. So when I close the switch, immediately what is the behavior of the voltage and the current in this circuit? If we look at our graph here, immediately you see the current goes up to a maximum value and then it begins to fall off all the way down to 0. As opposed to the voltage, which starts at 0 and builds up to a maximum point as determined by how much voltage is in the battery. We are talking now about our RC time constant. RC means resistor, capacitor, time constant. How long does it take this capacitor to charge? Our time constant, what it tells us is how long the capacitor is going to take to charge to 63.2% of the source voltage. Okay, so for our case here, if our resistor has a value of 1 mega ohm and our capacitor has a value of 0.1 UF, it's going to take 0.1 seconds to charge to 63.2% of the source voltage. If it has to charge fully, full 100 volts, it's going to do it in 5 time constants. To give you a better idea of our transient response and of our RC time constant and the charging of the battery, I have a little video clip courtesy Yves Pelletier, and it shows us the charging and discharging. Pay close attention to the rate at which the charged particles move. Okay, so once again, this video is courtesy Yves Pelletier. Now, as you could observe, the first electrons dashed out from one side of the capacitor real fast and made its way around to the other plate. If you were to look to your right at the graph, you'll notice that the line has begun increasing, and that line is also increasing at the rate at which the electrons are moving from one side of the capacitor to the next. Now, this process continues until the capacitor has become fully polarized, one side being more negative than the other. Now, if you were to pay attention to the curve, you'll notice that it started bending off in an exponential way. Well, it's starting to approach a point of saturation. If you look at the last electron there, you will also notice it's moving a whole lot slower than the first set of electrons moved. That's because it's reaching the point of saturation. Saturation, as you will recall, is a point that something is full and it cannot take any more. So as it approaches its maximum value, of course, it will naturally get slower and slower. Let's go ahead now and look at energy stored in the capacitor. We said that the capacitor has the ability to store energy. Well, let's go ahead and see if we could calculate how much energy a capacitor could store. For a simple circuit like this, once again, where we have a capacitor, resistor, a switch, and a battery, this capacitor is going to store 0.02 joules of energy. Okay, let's go ahead now and talk about the value of a capacitor. How do you determine the value of a capacitor? First, we have the surface area of the plates. And the plates, I mean these two metal plates here. The bigger the surface area is, the bigger the value of the capacitor will be. Second, we have the thickness of the dielectric. That's this portion here. Believe it or not, the thinner the dielectric is, the bigger the value of the capacitor will be. Third, we have the type of dielectric. Now this dielectric, I told you it's an insulation material. It could be air, it could also be glass, it could also be mica. These are all different materials that is used in making dielectric for capacitors. Let's look at now what is called capacitive reactance. We said before that a capacitor blocks DC, but it allows AC. DC meaning direct current and AC meaning alternating current. XC, which stands for the capacitive reactance, is equal to 1 over 2 multiplied by pi multiplied by the frequency of the AC voltage multiplied by the value of the capacitor in the circuit. If we look over here, we see we have a circuit here with an AC source of 100 volts at 10 kilohertz. We have a capacitor with a value of 100 microfarads. If we were to put these values into our formula, like what we have here, and work this down, we will notice that we end up with 0.159 ohms. What this is saying to us is that at this frequency of 10 kilohertz, the capacitor will put up an opposition that is equivalent to 0.159 ohms. Now for different frequencies of capacitance, for different frequencies of AC voltage, the capacitor will put up a different value of opposition. So that is worth paying attention to. It will not always be this. Okay, don't get it mixed up. There's a lot of people that is getting this mixed up. Okay, let us now look at capacitors being connected in parallel and series formation. If you remember from other videos, we did resistors in parallel and series. Now we're going to do capacitors. Now for capacitors, just the opposite happens as in resistors. That is something worth paying attention to. If we look at our series circuit, the formula that we use to determine CT, which stands for total capacitance in the series circuit, is either of two. Either 1 over C1 plus 1 over C2 plus ... and you know what ... means. If I were to add more capacitors in series, we will just go on. Or you can use the formula of C1 multiplied by C2 all over C1 plus C2. Now again I will repeat with this formula. If we had 3 capacitors here, then you will have to apply this formula twice. Okay? Keep that in mind. You will recall that from when we did the video on resistors. But for our case here, we just go ahead and use this one. Either of them is correct. Okay? So if we were to use this one and we were to substitute in the values for C1 and C2, you will see that our value, our total capacitance, comes out to be 1.33 microfarads. So connecting capacitors in series will give you a less value. Let's look now at our parallel combination. Our total capacitance for a 2 microfarad capacitor and a 4 microfarad capacitor, again, it's just the opposite for resistors, is C1 plus C2 plus dot 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 dot. And dot 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 means if we had 100 of them in parallel, it will be C1 plus C2 plus C3 plus C4, 5, 6, 7, 8, 9, all the way up to 100. So if we were to go ahead and substitute in the values, we see we end up with a total capacitance of 6 microfarads. So putting capacitors in parallel increases the value of the capacitor.